Let's look at something called the unit circle. The unit circle is a helpful tool that you can use to help determine special angle values. So let's go over that. Let's say I have a circle. Okay, so let's just draw a circle. And then what we say is the unit circle has a radius of 1. Okay, so there's a radius of 1. Now, to show you an example of how this unit circle can be helpful in special angles, imagine this unit circle is on the coordinate grid. So there's the y-axis. Here's the x-axis. Therefore, every point on the circle is inside one of the 4 quadrants. Quadrant 1, this being quadrant 1 and 2 and 3 and 4. Excuse me. Also, notice that from the center of the circle to any outside edge will also always be 1. Therefore, there are values on this circle with coordinates. Like, for example, this point right here on the x-axis only has an x value of 1 and no y value. So that point has coordinates 1, 0. Now, let's say I create an angle from that standard position, and I create an angle so that it goes up to create an angle of pi over 6. Excuse me. Okay, so this angle right here is pi over 6 in radians. Okay? Now, that creates a right triangle. If I drop this down, that can create a right triangle with the x-axis. And notice the length here, right? If we look at the coordinates of the point on the circle, then this length of the right triangle up to here would be its x value. This length right here would be its y value. Also, the hypotenuse, since it is on the circle from the center, also has a value of 1. This length is 1. It's a radius. Now, say I took, remember this is pi over 6, this angle. So say I took the sine of pi over 6. The sine of pi over 6, sine would be equal to opposite divided by the hypotenuse. The opposite side would then be this height right here, which is the y value, which would represent its y coordinate. So I'll write the y just up here. And the height divided by the height, the hypotenuse is 1. So it's just divided by 1. So it's going to stay itself. So I'll just leave it like that. But imagine it's divided by 1. Now sine of pi over 6 has an exact value. If you go look at our triangles, let me go back and create it, right? So we're used to doing this. So in radians, pi over 6 is equivalent to our 30 degrees. So if I cut this, this was 2, this is root 3, this was pi over 3, this was pi over 6, and therefore sine of pi over 6 would be this value, which is 1 over 2. So back here, sine of pi over 6 is 1 over 2. So the opposite side, which is that length right there, which we've already said is the y value in the coordinate, is a half. And notice it is also exactly equal to sine of pi over 6. That was sine of pi over 6 right there. If I looked at, say, cos of pi over 6 in this diagram, then that would be the adjacent divided by the hypotenuse, but the hypotenuse is 1. So the adjacent side, which is the x value here, this length, which is the x part of the coordinate, is just going to be cos of pi over 6. So that value right there is going to be cos of pi over 6. If we looked at cos of pi over 6, we'd calculate root 3 over 2. Okay, so this point right here, its x value is cos of the angle inside that's, we say, subtended on this, say, arc. The angle that's in, say, standard position is pi over 6. Cosine of that angle is the x coordinate, and sine of that angle is the y coordinate. Now I'm going to erase this, and I'm going to just show another example. So say I erase that. Okay, so say I draw this angle here, which is halfway through the first quadrant, which is an angle of pi over 4. That also has a point on the circle. And similarly, if I create a right triangle, this value here is the x coordinate, this value here is the y coordinate, this is still 1. So the hypotenuse is still 1. And say if I said sine of pi over 4, that's just the opposite again divided by the hypotenuse. So the opposite side again is exactly sine of pi over 4. And sine of pi over 4 is 1 over root 2. So the y value is 1 over root 2, which is the same as pi over 4, sine of pi over 4. And similarly, cos of pi over 4 is going to be the adjacent side divided by 1, which is just, so the adjacent side is, again, cos of that angle, which is 1 over root 2. So what we've got here is, we've just done 2 examples where if that point swings around on the circle, that the coordinates of that point are just these values. Okay, so the coordinates of all points look like this. Cosine of the angle in standard position, comma, sine of the angle in standard position. And that's always true since the radius is 1. So if I have a circle radius 1, any point on that circle will have cosine as its x value, sine as its y value. Okay, now this can be very useful because using our triangles and having this triangle is very similar to the triangle, let's say, flipped across here, and we can also use the cast rule to develop and use this this circle to easily remember or use it as a tool to come up with values like what is the exact value of sine of 2 pi over 3, or what is the exact value of cosine of 5 pi over 6. So sometimes it's hard to remember, and it's quite possible that you can convert those angles to degrees and then use your knowledge of the cast rule and those to develop the exact values. I find it a little bit quicker to use the unit circle, and I'm going to show you some examples. Before I do that, I'm going to kind of quickly go through and develop a kind of like a resource you could save or copy out, so that would show you some of these exact values, and it's going to incorporate where certain x values are negative and certain y values are negative. So I'm going to go around the circle, and on the circle I am going to write down the angle that, say, we've just done this one. So I'm going to write the angle right underneath the arrow. So this angle that, say, goes up. Okay, I'm going to erase this in a minute because I don't want it to get all messy, because it can. This angle is going to be pi over 6. And here I'm going to write the coordinates, which will be sine of pi over 6, or sorry, cos of pi over 6, comma sine of pi over 6. And that's going to happen all the way around. And so if we say sine of pi over 6, we knew was a half from our special work the other day. Cos of pi over 6 is root 3 over 2. Now also, I like to use this, and this is how this is going to be helpful. Okay, so when I drop this triangle down, I usually won't draw the triangle, but I drop the triangle down. If you remember 2 ideas, that root 3 over 2 as a decimal, rounded off, is about 0.86666, so I could say 0.867, and a half is 0.5. So I use this idea that 0.867 is bigger than 0.5. This length in the triangle is bigger than this length, and so therefore root 3 over 2 is bigger than a half. So root 3 over, this is all the long lengths when we create these triangles are the root 3's over 2's. All the short lengths when we create these triangles are the halves. Now also notice when I drop this down, this is really the same triangle because this 30 and 60 triangle occur together. So this is kind of this triangle rotated up. So now this is the short length, and this is the long length. So the y is then root 3 over 2, and the x is a half. And that corresponds to our angle of pi over 3. That's our 60-degree angle right there. This is our 30-degree angle right here. And notice the coordinates are just flipped. We're going to use that idea to help get these values out. Okay, so what I'm going to do is I'm going to erase those triangles that I drew, and I'm going to go around the circle and I'm just going to fill in the values. If you notice also on here, sometimes it's hard to think about sine of pi over 2 and cosine of pi over 2, but notice this. If this is the x axis, then the x coordinate of this point up here is 0 for sure. And the y coordinate is just whatever the length is here, which is, we already know it's 1. So we can also use this idea to say, look at cos of pi over 2 is 0. Sine of pi over 2 is 1. I also like to do it this way when I count, to figure out what angle is which. Notice that pi over 3 is really this 2 pi over 6. So what I do is I like to count by pi's over 6's. Okay, so look at this. Like, there's a pi over 6, and I skip this one because it's not a multiple of pi over 6. So pi over 6, that's 2 pi over 6. Notice this is 3 pi over 6 because 3 pi over 6 simplifies to pi over 2. This would be 4 pi over 6, 5 pi over 6, 6 pi over 6, and that's how we get pi, 7 pi over 6, 8 pi over 6. Notice how I skipped the pi over 4s, the halfway points. That was 7, that was 8. This is 9 pi over 6, this is 10 pi over 6, this is 11 pi over 6, and 12 pi over 6 is 2 pi. So that's how I do the counting. I will then notice if this was pi over 6, 2 pi over 6, 3 pi over 6, this is 4 pi over 6, but 4 pi over 6 simplifies to 2 pi over 3. So I will write it in reduced form. Okay, now I've gone through and I've put all the multiples of pi's over 6's in as special angles. Okay, so now notice if you copy this out, now you can pause it, copy this out, and you can use this as a resource when you're doing special angles, and you'll get, now when I do them on the board, I will show you that I draw a circle and count, and I'll show you how to do an example like that in this video, or sorry, the next video. But for example, if I wanted to know what the sine of 4 pi over 3 is, I could say find 4 pi over 3 on it, and that's this big angle right here in radians, right? So from standard position, we're looking at 4 pi over 3 is a big angle here, and therefore there's where 4 pi over 3 lands. The coordinates here correspond to here. So this is the cosine of 4 pi over 3. This is the sine of 4 pi over 3. And notice they're both negative, and that's the sine of an angle bigger than 180 degrees, and say this third quadrant is a negative, and the this one, and the cosine of an angle in this quadrant is also a negative by the cast rule from last year. So we will remember these values by just kind of looking them up. Remember that that's going to be the cosine, that's going to be the sine. I'm going to go through now and in a different color write down the pi over 4s, multiples of pi over 4. So there's pi over 4, and notice the pi over 4s are all going to be 1 over root, right? They're all reflections of the same triangle in the different quadrants. Okay, so I'm going to rewrite these, but they just have different signs. So this is how I would count it. This is pi over 4 here, and then notice this one matches up with a pi over 4. This is 2 pi over 4. And then this is 3 pi over 4 over here. And this would be 4 pi over 4, which is pi, and this is 5 pi over 4. And then 6 pi over 4 is still 3 pi over 2, and then this one is 7 pi over 4. And then we got 8 pi over 4, which is 2 pi. And there's the unit circle. Copy it out, print it off. In the next video I'm going to show you how I can redraw this quickly. And I don't draw all the parts, but redraw it quickly to develop or to find out those special angles.